Alex Gaynor. Together with Paul, we are the maintainers of the Python Cryptographic Authority. My day job is as a member of the technical staff at Anthropic, though I'm here speaking entirely in my personal capacity. And before that, I was the Deputy Chief Technologist at the United States Federal Trade Commission. I've also maintained lots of other open source projects over the years.
And as Alex said, I'm P.Kehrer. Other than being co-maintainer with Alex, I work in Oracle Cloud Infrastructure as a cryptographic architect who moonlights as an AI data center person these days. But the opinions expressed here are strictly in my personal capacity as an open source maintainer. Before my current job, I ran the cryptographic practice at Trail of Bits.
Cool. So the Python Cryptographic Authority, or pyca as we'll call it, is an open source umbrella for several widely used cryptography projects in the Python ecosystem. While we maintain several projects, our flagship project is very cleverly named Cryptography, and we'll call it pyca Cryptography to try to make that clear. It's one of the most widely used libraries in Python. We're usually in the top 20 most downloaded libraries. We're used by certbot, which is the original Let's Encrypt command line client. Every single major public cloud's command line tool uses us, as do tools like man-in-the-middle proxy and SaltStack. And in a typical month, we have about 500 million downloads. I'm telling you this, A, to boost up our egos, and B, to give you a sense that we're very widely dependent on in the Python ecosystem, and that kind of wide use shapes how we think about building pyca cryptography and kind of all the things we'll talk about for the rest of the talk. pyca cryptography scope is pretty broad. We offer kind of all of the core typical cryptographic algorithms like AES or RSA or Blake2 or scrypt. We also have kind of higher level cryptography recipes like Fernet, which is an authenticated encryption format. And we have all of the kind of typical serialization formats like PKCS7 and PKCS12, as well as kind of the entire X509 cinematic universe, including things like parsing and signing and path building and validation and CRLs and OCSP. The one thing we don't have any APIs for is TLS. So we're about 12 years old now, and since day zero, we've used OpenSSL to provide all of those core cryptographic algorithms. So we're big consumers of libcrypto, but as I said, no TLS, so we don't really use libSSL along the way. And along the 12-year journey, we've changed a lot about how we use OpenSSL. So I'm going to start by kind of walking you through the history to give some context for what we'll be sharing. So in the very beginning, OpenSSL wasn't actually the only source of cryptography we had. Originally, we had this idea that we'd support multiple pluggable backends, so you could get your cryptography from either OpenSSL or from Common Crypto on Mac OS or from CryptoNG on Windows, and it all have kind of the same Python API. Users wouldn't have to know the difference. And we tried this for the first couple of years, and what we discovered is A, these libraries have incredibly different APIs. It's not like we had any shared code between these. We were really just writing 3 different versions of our library. B, these libraries have lots of different bugs. And so we were spending a lot of time reporting bugs to different libraries. In the process of implementing AES GCM for Common Crypto on Mac OS, we reported something like a half a different bugs that were just specific to Common Crypto. C, each of these libraries had different subsets of functionality, which led to a pretty confusing experience for our users. And lastly, users didn't actually want pluggable backends. They wanted us to pick one. After all, we were the cryptography experts. So we got rid of multiple backends pretty early on. And when we gave up on that, we standardized on just OpenSSL. It was always the most complete backend. We never had any functionality that OpenSSL didn't support. It works on every platform, and it's really the de facto open source standard for a cryptography library. And the way we use OpenSSL in Python is we used a library called CFFI, which simply put lets you call C APIs from Python code. From the beginning, we were supporting multiple OpenSSL versions, 09A to 101, as I date ourselves. However, originally, we didn't commit to supporting any of the OpenSSL forks, which at the time were LibreSSL and BoringSSL. However, along the way, not supporting LibreSSL became pretty untenable. We'd become sufficiently popular in the Python ecosystem that not supporting LibreSSL was having like significant user experience impacts for people on OpenBSD and Alpine Linux, which at the time was using LibreSSL. And in practice, what it meant is those platforms were carrying a bunch of their own patches to add support for LibreSSL to pyca cryptography. So eventually we added LibreSSL support. Years later, we also decided to officially support boring SSL because we knew that Google was carrying also their own patches to add boring SSL support. And in the last couple of months, we've also added support for AWS libcrypto as well. I mentioned that in the beginning, we used CFFI to call into OpenSSL. In 2020, 5 years ago, we made the decision that the time was right to start adopting a memory-safe programming language for cryptography. CFFI provides all of the safety of C, which is to say almost none. You can buffer overflow with CFFI, you can use memory after it's been freed, you can access the wrong union member, kind of all of the typical C pitfalls are now available to you in Python. We made the choice that pyca cryptography was going to become a Rust project, and Paul and I gave a full talk about our experience migrating to Rust at PyCon a few years ago. But kind of for this audience specifically, I'll describe that what this meant is that we now use Rust to create a Python extension module, and in our Rust code, we use the Rust OpenSSL library to call into OpenSSL. Rust OpenSSL, of course, uses OpenSSL C API, and so Rust OpenSSL is responsible for making sure it binds things correctly and exposes safe Rust APIs. But from our perspective, we now get an OpenSSL experience where memory corruption bugs aren't possible in Rust code. And so at first, this didn't actually change very much about our library. We took things that used to be using OpenSSL with CFFI, and now they were using OpenSSL with Rust OpenSSL. However, once we kind of had the pieces in place to write Rust code, we began migrating some of our functionality from using OpenSSL to using some of our own bespoke Rust code. So in particular, we migrated all of our X509 related code, including parsing and signing and path building, to be written in pure Rust, built on top of our own Rust ASN1 dir library. So when we do something like create a certificate, we'll still use OpenSSL's EVP P key to actually sign the certificate. But what it's signing is simply the raw bytes that are generated by our ASN1 library. We did similar migrations to things like key loading with PKCS1 and PKCS8. And these are all built on top of the same Rust ASN1 dir library. And we'll talk later about some of the benefits we think we got from this. I want to briefly describe how we distribute our project. Like many projects, we have both a source distribution as well as a binary distribution. And the source distribution users can compile themselves. The binary distribution is precompiled. In Python packaging, we call binary distributions wheels. And so we ship binary wheels for ARM64 and x86-64 Mac OS, x86, x86-64 and ARM64 Windows, x86-64, ARM64, ARM v7L, and PowerPC 64 Little Endian, GNU libc Linux, as well as x86-64 and ARM64 Muscle libc Linux. In short, a whole lot of platforms. For all the platforms where we ship wheels, our wheels contain a statically linked copy of OpenSSL, and we issue a new release of pyca cryptography anytime OpenSSL performs a release, upgrading that statically linked version. When OpenSSL does a security release in particular, we'll generally do a pyca cryptography release on that same day. And what we see is, within 1 day of a release, we generally see something like 50% of our users' downloads are from the newest version. And the vast majority of our users rely on these binary wheels. And so we do the static linking because there's no way to distribute a portable binary, particularly across many Linux distributions, that dynamically link against the platform OpenSSL, because they're all different versions, different paths, et cetera. And of course, other platforms like Windows or Mac OS don't have a system OpenSSL you can link against at all. One of the consequences of this is that we almost certainly have the largest pool of people who are running the very latest OpenSSL patch release at any given time. So I've walked you through how we use OpenSSL, what we use it for. I want to step back and talk about what we think makes a good cryptography library. Having a shared understanding of what our desiderata are is important, I think, because it helps us have a clear conversation on how well we're doing at accomplishing our goals and whether we're making good trade-offs along the way. So I'm a little embarrassed to say we've never actually written down our beliefs about what makes a good cryptography library. for pyca cryptography. However, we did write them down for our Rust ASN1 library, and so we'll go through those because I think those are a good approximation of what we want for a cryptography library. So the criteria I'll walk through are in order, which is to say we want all of these things, but when there's a trade-off, we try to prioritize the things higher up on the list in the trade-off. We also try to work pretty hard to find creative ways to find Pareto optimal choices, that is, ways that we don't have to make a trade-off at all through clever engineering. And one of the things you'll hear as I talk through these is that we're focused both on kind of the properties of the libraries itself and the ways its APIs encourage particular outcomes for its users. So our highest priority is security. Maybe not a surprise. People use cryptography libraries to try to build security functionality in their applications, and therefore it's critical that a cryptography library never regress security by having vulnerabilities. And so this means we care about the presence of vulnerabilities, but also about systems design approaches that prevent classes of vulnerabilities. So for example, you might have things like usage of memory-safe languages or formal verification of cryptographic algorithms as supporting this. We also care about things like whether a project has APIs that encourage secure outcomes for users. Do the APIs have dangerous defaults? Are there obvious ways of using the API that are in fact kind of incorrect or lead to bad security outcomes? And these kind of security considerations come above everything else for us. Our next priority is correctness. It's great for a program not to have vulnerabilities, but people also want things to work. And of course, with many aspects of cryptography, correctness and security go hand in hand, where deviations from a specification might not merely impact correctness, but also impact security. We also favor having pretty strict interpretations of specifications and rejecting inputs with even minor deviations from what the spec allows. Historically, lots of people appealed to things like Pastel's law as an argument for having lax parsing that accepts things beyond what the spec allows. However, what we've found is that once you start accepting things beyond the specification, you get kind of a snowball effect where you accept more and more things that don't actually meet the specification. And sort of every other implementation in the ecosystem is also forced to accept these deviations. So we think the history of HTML4, which effectively became unparsable with all the differences between browsers, is a good example of something we want to avoid in comparison with something like HTML5, where the specification defines precisely how every browser must parse it, and browsers tend to adhere to that. The history of the web PKI, before linters became ubiquitous, is another example of places where we were seeing deviation spread. Performance is also really important. Unfortunately, much as we'd like people to design for security from the beginning, cryptography is frequently added to systems kind of after the fact that weren't originally designed. As a result, the amount of overhead cryptography adds significantly acts as a significant criteria for whether organizations will introduce cryptography. And if we want to build secure systems, we need to make the cost of security as low as possible, and unacceptably high overheads to performance are a frequent impediment and a kind of reason organizations will give for not introducing cryptography at all. When we think about kind of the path the web has taken towards going HTTPS only, a key part of that we know is the path towards improving the performance profile of TLS, things like limited round trips on handshakes, as well as supporting low power devices that don't have dedicated AES instructions. The principle of generality means that for Rust ASN1, we try to support the full scope of valid use cases within DIR. I'm not going to spend a ton of time on this point because we don't really talk about it more for the rest of the talk. And finally, to the extent compatible with all of these other principles, we try to optimize for ergonomics and ease of use in our APIs. Note that we think a lot of features of API design are actually dictated by security or correctness or performance. But to the extent there's not, we want to make our APIs easy to use. One consequence is that we often have kind of verbose APIs that require users to specify lots of parameters because we want to make sure we're never in a position where we've made the default parameter something insecure and now we can't change it due to backwards compatibility. So you know how we use OpenSSL and what we want from the kind of platonic ideal of a cryptography library. Now Paul's going to talk a little bit about the challenges we have and continue to have with OpenSSL.
All right, folks. So let's talk a little bit about testing. I want to start by acknowledging that the quality of testing in OpenSSL is substantially higher than it was a decade ago. However, over the last several years, we've seen several things we think can be significantly improved. First, the general coverage of the API surface area is not particularly comprehensive. Combined with very complex APIs that can be used in numerous different ways, especially ones that have like multiple steps for initialization and things of that nature, this can cause major development challenges. This was extremely noticeable during the OpenSSL 3.0 development cycle, as the project kind of repeatedly ran into situations where you wanted to make changes, but you didn't have the testing to know whether the given change broke or altered things that users were depending upon, which resulted in longer alpha cycles than we expected, and then longer beta cycles than we expected, and generally just took multiple years longer than was originally planned for. Coverage can also be affected by architecture and OS-specific code. OpenSSL is a complex project which supports numerous architectures and operating systems. While not all of these are feasible to test in the OpenSSL CI, obviously, tools like Intel SDE and things of that nature can be leveraged to get far more comprehensive testing of various assembly paths. Test flakiness has also been an issue for the project. In fact, still is as of this morning when I took a look. But OpenSSL 3.04 contained a critical bug in the RSA implementation when used on AVX 512 capable CPUs. This was actually caught by accident in CI, but since it only crashed when the underlying CI runner had AVX 512 capable CPU, which many of them did not, the crashes were kind of ignored as CI flakiness at the time. It's been 3 years since that incident, but unfortunately a willingness to merge when tests are failing because they are presumed to be flaky is a continuing source of risk for the project. For example, the day we created these slides, which was about 3 weeks ago at this point, 5 out of the 10 commits that landed that day actually had failing CI checks. And as of yesterday when I took a look, all cross-compilation had failed for several days on every single merge to main. So bug fixes are also not consistently accompanied by tests. Unfortunately, without tests, we can't confidently prevent these regressions, and future changes become riskier, and we end up in the same kind of situation of not knowing whether or not something is actually broken or not. The same thing slowed down the refactors for the OpenSSL 3.0, and now that the 4.0 effort is underway, I think there's another opportunity to take a look at this. But engineers can't rely on tests to explain library behavior now, which means that no changes are ever fearless inside this code base. Tests need to be treated as a non-negotiable part of fixing bugs, just like we always need to have tests for new features. As a relatively concrete example, Alex and myself, over the course of the last several years, have definitely replied on several OpenSSL PRs with just during a bug fix, with just the question of, could we add a test? So how do we improve? So Alex and I consistently joke with each other that the Python Cryptographic Authority is actually a CI engineering project masquerading as a cryptographic one. However, this joke is rooted in the truth that we believe spending time on CI provides enormous payback. I will note that also in the days we've been here, we've mostly spent our time on CI. So we suggest that OpenSSL look deeply at their CI practices and dedicate significant engineering resources towards improvement. Things like combining coverage measures across your jobs, gate your bug fixes and features on coverage requirements. Like these are things that are enforceable as a GitHub merge requirement. Improve the performance on each job so the feedback loop is faster, right? Like when the jobs take forever or you have issues with that, it becomes very easy to say, we're not going to worry about that one right now because I don't want to wait 6 hours for this to tell me the answer. You should hunt down the CI reliability issues and fix them. And then set those merge policies that prohibit merge without a clean CI. Like this is genuinely a hard thing to do, but it will really pay off over time. And then you should look at expanding your testing into new areas. For example, I know Boring has done some work on doing ABI testing for the assembly, and Intel SDE and similar for instructions that CI doesn't have natively available would also make a lot of sense. And of course, I believe this is one, I had it on the list, but I think you folks are already discussing, which is enforce your style with linters. We don't need to have style arguments. We can just have linters that do this for us. This list is intended as a starting point because CI work ultimately never ends. At my employer, we use it in terms of the like Python Cryptographic Authority. No, we do not use it at this time. The question was whether or not we used Intel SDE in our own test suite at this time. You should ask some questions at the end. We have some stuff around our CI for that. So, Alex, I believe this is your slide here.
So I mentioned earlier that we migrated some of our key parsing and X509 code paths from OpenSSL to our own Rust code, and we got some performance wins from that. In talking about performance, I want to start by kind of sizing those wins. So migrating X509 certificate parsing from OpenSSL to our own Rust code sped up the certificate parsing by 10x. It was a 10x performance win. When we migrated public key parsing from OpenSSL to Rust, that sped up X509 path validation by 60%. Note what I said. Migrating just key parsing, public key parsing, SPKIs, sped up the entire end-to-end X509 path validation by 60%. That's how large the overhead of parsing in OpenSSL was. So it'd be fun to tell you that these wins were a result of like clever micro-optimization. We spent days with a profiler, handwritten SIMD, things like that. But in reality, our dir parsing performance is completely a result of doing simple things that work. We avoid locks, we avoid hash tables, we avoid allocations, indirect calls, and copies. And mostly I want to communicate, we don't have time to fully talk about performance, but I just want to communicate better performance as possible. I also want to say what we're not talking about. We aren't talking about the kind of performance of core cryptographic kernels like the innermost loop in AES GCM, because we know those are, in fact, heavily optimized assembly where folks have spent days doing the clever micro-optimizations. Our concerns are about the things that exist all around that, parsing keys, setting up data structures, state machines, driving that assembly. So prior to OpenSSL 3, OpenSSL's performance in kind of all of these areas is fine. I don't know that it was off the charts remarkable, right? Clearly not as optimized as those hot assembly loops, but it never caught our attention and was never a problem. So in OpenSSL 3, the performance of these kind of dir parsing operations regressed massively. A few years ago, I filed a bug because parsing an elliptic curve public key had gotten 5 to 8 times slower from OpenSSL 111S to OpenSSL 3.07. And in fact, the reason we noticed this at all was that our continuous integration had gotten slower as a result of key parsing getting slower, and we noticed our CI getting slower. But more than the regressions, the reaction I got was what really stood out. The reaction was that some amount of performance regression was expected with OpenSSL 3, and while maybe some optimizations were possible, we shouldn't really ever expect it to get as fast as it used to be. And since then, performance has improved. Now loading an elliptic curve public key is only 3 times slower than OpenSSL 111. We think these regressions are unnecessary. As I shared, we now do our own key parsing, and our performance is back to kind of the same order of magnitude as OpenSSL 111. So we see it's possible to parse keys into EVP keys so much faster. And unfortunately, some of the approaches OpenSSL has taken to get those performance win back have also added a lot of complexity. And kind of the apex of that complexity is the usage of RCU, or read copy update, which is a memory management technique. And it's also had several subtle concurrency bugs because of how complex it is. So kind of looking at the saga end to end, what I see is kind of the way providers were designed and some of the other OpenSSL 3 design changes had a lot of significant new immutable state, indirect calls, and locking. And as a result, you got some performance regressions. But to compensate for that, the solution was to add new caches in addition to mechanisms like RCU. And so those brought back some of the performance wins, but kind of end to end, you had a big increase in complexity and still a performance regression. So it's my hope that as the OpenSSL core team looks towards OpenSSL 4, they'll consider addressing some of these issues closer to the root, such as changing the design of the provider's abstraction or removing it entirely, such as removing the ability to kind of mutate OpenSSL's global configuration at any time. This is maybe a controversial proposition, but I don't think there's a lot of value in being able to redefine what SHA-256 is at any point in a program's execution.
So OpenSSL's API design spans nearly 3 decades now, and it's well known that over that time, the API has grown in suboptimal ways. OpenSSL 1.1.x made significant strides by opaquing numerous structs, but some of the changes in 3.x have been a bit more challenging for us. So OpenSSL commonly allows mutation of structures that should ideally be immutable. For example, X509 certificates, CRLs, and private keys. Additionally, many key types require multiple steps to perform operations, necessitating mutable keys that can be in partially initialized states. This mutability creates opportunities for accidental corruption, race conditions in multi-threaded environments, and potential security vulnerabilities where an attacker who gains partial control could subtly alter key parameters to weaken cryptographic operations. Immutable keys would provide compile time and runtime guarantees that once a key is established, it remains constant through its life cycle. It's a property that simplifies reasoning about security, enables a bunch of better optimizations, and it prevents entire classes of bugs. Much of this current state is a result of OpenSSL's long legacy, but with OpenSSL's for the transition of this is another ABI break. There's another opportunity to have a conversation about can we move this bar forward. Another example in OpenSSL's long history, something I know the OpenSSL developers are very, very aware of, is memory ownership. For many objects, it remains ambiguous whether a function consumes ownership, implements a reference count, or borrows a pointer. And so developers are forced to kind of meticulously trace through the source code to determine when they're responsible for freeing the memory. The library inconsistently, mostly due to historical reasons, mixes reference-counted objects with manually managed resources, and functions that appear similar may have wildly different ownership transfer behavior. This ambiguity is actually compounded by the prevalence of functions that return pointers to internal structures, where it's unclear whether those pointers remain valid after certain operations or whether modifications to returned objects will affect that parent structure. The project has taken some steps to address this, but like get/set, get0/set0, get1/set1, and now the new OSSL param types are all things that every OpenSSL user actually has to contend with on a daily basis. OpenSSL 3's introduction of OSSL param structures actually represents a significant shift in API design. While we haven't seen a documented rationale, we generally believe it to be intended to be a more flexible and extensible parameter passing mechanism that allows arbitrary providers and the sort of flexibility that you would expect out of a system like that. However, these structures force developers to construct arrays of key value pairs with explicit type information for operations that, frankly, we believe would be generally better as simple function calls with type parameters. The result we see is kind of a verbose, error-prone set of code where simple tasks like setting an algorithm or a key size now require multiple lines of OSSL param initialization, manual string matching of parameter names, and careful attention to type correctness. For most common use cases, this added abstraction layer provides, from our perspective, no real benefit over a direct type-safe function interface that you would have seen in OpenSSL 1.1.1, and instead creates a substantially steeper learning curve and more opportunities for subtle bugs. As a quick illustrative example, on the left here, we have a function that uses the new OpenSSL 3 APIs to perform an ML-chem encapsulation from a serialized public key, returning a shared secret in a ciphertext. And on the right, we have boring SSL's API for the exact same operation.
In addition to OpenSSL's public API becoming more complex, what we've often found is that OpenSSL's internals have also grown more complex at the same time. As we like to think sophisticated consumers, we often reach for OpenSSL source code to understand exactly how APIs work. Is this parameter copied? Is it by reference? How long is it kept alive? Unfortunately, a lot of the new abstractions and indirections in OpenSSL 3, what we found is that it's become significantly more difficult to go from kind of the public API function name to where the real implementation is. We often find that an OpenSSL public API is kind of a facade that sits in front of several layers of indirect calls, and that these are challenging to trace through. And this makes using OpenSSL correctly much more difficult and often leaves us extremely frustrated. We think having the source code be readable is essential for consumers, and the situation is only growing more fraught. For example, many source files now are no longer even technically C files. There's now a custom preprocessor to handle some of the OSSL param API usage. To give a really concrete example of this, in the process of writing that last slide, we needed to figure out which header defines the OSSL p-key param pub key constant. And the answer to this question is it's not in the OpenSSL documentation. There's a couple examples that use it, but none have the include. So we moved on to grepping the OpenSSL source tree, and simply put, searching for that value in the include directory doesn't find anything. My editor's go to definition functionality also didn't turn anything up, and the example we found after 5 frustrating minutes is that there's a Perl script that will generate a bunch of these defines as part of the build process. This is not an isolated example. It's just this week's example. This is what tends to happen every time we try to read the OpenSSL source code. And we really can't overstate the extent to which these sorts of complications make using OpenSSL quite unpleasant for us in ways that don't happen with forks like boring SSL. On a different note, many of OpenSSL's parsing APIs are fairly lax in what they accept. Many will accept BER, even where dir is intended. Version fields are not checked for validity, and bug reports about OpenSSL emitting invalid dir are marked as feature requests rather than treated as bugs. As we've adopted our own parsing code, we've become stricter on effectively every axis in what we will accept, rejecting basically all deviations from strict dir, except in an exceptionally limited number of cases where we got sufficient reports from users to know that being strict just caused too much ecosystem breakage to be possible. Along the way, we've also had to push back on many commercial vendors who come to us and say, hey, OpenSSL parses this, why are you rejecting it? You broke us. And what we tell them is, we reject it because it's not valid. You are the one shipping the broken thing. You need to fix your software. We consider it a bug that we ever accepted this. And so for us, the issue with OpenSSL's laxness is not really first-order bugs, but rather this kind of second-order effect, where OpenSSL is so popular and so ubiquitous that when it accepts something that's actually invalid, people just assume it must have been valid, and the spec kind of becomes vestigial. People can no longer rely on just reading the spec to know it's valid, and we think that's bad for the kind of long-term health of the broad cryptographic ecosystem.
So OpenSSL has had a variety of forks. We've chosen to support some of the most popular, specifically LibreSSL, Boring SSL, and AWS-LC. These forks all have a shared, mostly OpenSSL 1.1 compatible API. However, as OpenSSL adds new features like PQC or Argon2 ID, which are things we obviously would very much like to consume, the APIs of these forks are increasingly diverging. This puts us in a bit of a difficult position, as supporting, for example, MLChem results in a minimum of 2, but as many as 4 different APIs that we now actually need to write code for. In general, we've found that the forks are actually loosely aligning around consistent APIs for new APIs like PQC, but thus far there actually appears to be limited appetite on their side for implementing the OpenSSL 3.x compatible APIs, possibly for the reasons discussed on our slide, although I do not know that. So, in another part of this talk, Alex talked a bit about what we want from an idealized cryptography library. So now let's talk about what we think a real-world general-purpose cryptographic library like OpenSSL should actually focus on.
When OpenSSL was first created nearly 3 decades ago, if you wanted to write high-performance code that could be run on many platforms and embedded in numerous other programs, you didn't have many choices. You effectively had C, maybe C++, and little assembly. Even in 1998, C's security pitfalls were well known, but there wasn't much you could do about it. Your alternatives were slow languages with expensive garbage collectors and large runtimes that meant you couldn't use them in many places. However, in 2025, the landscape has changed significantly. I talked about the Pareto frontier earlier. Rust and other innovations in programming languages have shifted it out significantly. There's no longer a hard trade-off between performance, embeddability, and security. We can have all 3 at once. Simply put, we believe in this decade, projects that have real threat models, like cryptography libraries, and that are written in memory-unsafe languages should be making plans and executing on migrations to memory-safe languages. In 2023, the White House published a national cybersecurity strategy for the United States that included an emphasis on memory-safe languages. And in 2024, the US NSA, FBI, and CISA, alongside the Canadian CSE, the UK NCSC, Australian ASD, and UK NCSC, issued a report calling for companies to adopt roadmaps for migrations to memory safety. We know from our own experiences that while migrating a large project is not a simple thing, it's extremely possible with incremental approaches and robust testing. Being a cryptography library does have some interesting challenges on this front. Because most programming languages, including C and Rust, don't specify anything about side channels, writing an assembly is the only way to write certain core primitives securely. However, by volume, even a cryptography library is overwhelmingly things like serialization and state machines, which have significant risk for memory corruption vulnerabilities and no obstacles to being in a memory-safe language. We think going forward, memory-safe programming languages will become table stakes for projects that are committed to security.
So many large-scale systems, especially distributed ones, are challenging to test. In contrast, cryptography libraries are in many ways pretty easy. While there's some nuance in the RNG components, for the vast majority of code, testing all branches is actually largely straightforward. With sufficient effort, it's possible to achieve and maintain 100% coverage in these scenarios. Even things like CPU microarchitecturally specific assembly can be tested using tools like Intel SDE, as we discussed earlier. But if those tools don't exist for various esoteric architectures, I would encourage OpenSSL as a project, has a lot of clout in the industry, and they could ask the vendors to require them ask the vendors to create them and require them as a condition for inclusion. But coverage is only one metric. Libraries should also be incorporating and consistently updating / contributing to projects like Wishproof, which maintain test vectors of known attacks, spec inconsistencies that can lead to security issues, and various other implementation bugs. RFC test vectors, frankly, rarely contain interesting edge cases, and assuming a few positive and maybe a negative test case is sufficient may mask relatively major implementation flaws. Additionally, in the past 10 years, formal verification has gone from academic novelty to practical reality for some subsets of cryptographic problems. Forks like Boring and AWS LC already have incorporated some formally verified implementations. And on the AWS LC side, they have some automated reasoning that they're doing as well on some of their microarchitectural specific assembly for increasing our insurance. Any project implementing cryptographic primitives needs to be evaluating these tools for either proving correctness of existing code or generating code from a formally verified model at some point. I will say the latter introduces more potential build complexity, but it doesn't suffer from potential implementation drift from the proof, which is a risk in some of these scenarios. A narrow API surface. It's one of the most powerful tools for creating maintainable, secure cryptographic libraries, right? You expose fewer functions, and there we go. There we go. By exposing fewer functions, data structures, and configuration points, you just dramatically reduce your attack surface. It limits the ways your users can misuse your library, and you preserve the freedom to refactor your internals extensively without breaking your compatibility. Obviously, OpenSSL 1.1.1's opaquing and some of the stuff that's been done since then is partially towards these sorts of concepts. When APIs are narrow and well-constrained, every function becomes easier to test, and audit, and reason about. Minimizing mutable state and global configuration, which we discussed previously, also reduces the cognitive load on both maintainers and users. Functions are far more predictable, thread safety issues are lesser, and the risk of subtle interactions between seemingly unrelated API calls drops significantly. While it may feel limiting to reduce those options, a focused API ultimately empowers users by making the correct path obvious and the dangerous paths impossible, ultimately leading to more secure implementations in the field. The goal isn't to restrict the capability, but to channel it through well-defended, thoroughly understood entry points that can evolve safely over time. When we talked about our principles earlier, we stated that security and correctness were more important than performance. But of course, performance still matters. Performance in cryptographic libraries really does need to be there from the ground up. It's very difficult, if not impossible, to bolt it on after the fact. The fundamental data structures, memory layouts, and algorithmic choices made in the initial design determine whether you can later exploit SIMD, achieve cache-friendly access patterns, or minimize your memory allocations in the hot path. Once you've committed to an API that requires multiple round trips for a single operation, or data structure that necessitate frequent copying and transformation, no amount of micro-optimization is going to recover the performance lost due to those architectural decisions. The layout of your context structures, the granularity of the operations exposed to the users, and even the choice of whether to support in-place operations versus separate input-output buffers. These early decisions cascade through the entire library and determine whether or not you can achieve zero-copy designs, efficient batching, and hardware acceleration. By the time your users are complaining about performance, the API contract is often set in stone, and you're left applying superficial optimizations to a foundation that was never really designed to be fast.
Thank you all for listening to us, and thank you to the OpenSSL project for how far it's taken us in these last 12 years. We're hopeful this talk has provided some food for thought and inspiration for continued improvement in OpenSSL, and we're now happy to take questions for however much time we have. Thank you all.
Thank you very much. The question is, how strictly did you follow the principles you told at the end of the presentation when you implemented your own certificate parsing and so on that you did?
Yeah, so we tried hard to follow these principles. I will also say these principles are things we have learned and discovered in 12 years. So the older the API is in pyca cryptography, the less likely it is we got things exactly right. But I think our certificate APIs are a pretty good example of following these. We're incredibly aggressive about, I use our X509 path validation implementations. That's relatively recent. We are incredibly aggressive about having extremely robust testing. We built a brand new X509 testing framework entirely that can be tested against multiple implementations to ensure correctness. We used memory-safe programming languages. We use any external test cases we can get our hands on, such as what's Netflix's test suite called?
Better TLS is their website. I can't remember what the test suite's
called. The Better TLS test suite from Netflix. And then we tried to build on a foundation of performance, as well as adhering to kind of correctness approaches. Like, for example, Ryan Sleevy's mantra that any validation that's part of path building needs to happen in the path building and not afterwards. So we think we've done a reasonable job adhering to it, but we're also always open to constructive criticism.